Okay, in this video we'll be talking about localization. So basically how your vehicle or robot figures out its position relative to the world or some sort of map. So what we'll be going through, first we'll be tackling, just getting a general overview of some localization solutions that there are. We'll be talking about the Global Navigation Satellite System, GNSS, and other types of solutions for localization. Then we'll be diving into simultaneous localization and mapping, SLAM, to basically figure out how to do very precise, very accurate localization. And third, we'll be talking a little bit about visual SLAM, VSLAM, which is then basically SLAM done with a camera. And the learning outcomes of this session basically aligned with the contents. So first of all, after this video, you should be able to identify the key techniques and methodologies that exist for localizing a vehicle. And secondly, you should have knowledge of the basic steps of implementing simultaneous localization and mapping based on a LiDAR sensor and the point clouds that it provides. Okay, so first jumping in to the what type of localization systems there are. Of course, the first thing that often comes to mind when thinking about localization is Global Navigation Satellite System, so the GNSS. Typically, generally when people are talking about these systems, they are just talking about GPS. But it should be noted that GPS, the Global Positioning System, this is basically the Global Navigation Satellite System operated by the US. So the sort of a correct term for overall talking about these systems is Global Navigation Satellite System. So what we are talking about, everyone is familiar with this technology. It's something that you have on your phones, all types of smart watches and so on. So basically we are talking about having a receiver which is communicating with satellites orbiting the Earth. And basically what the receiver is doing, it is figuring out its position relative to these satellites, and this way figuring out its position on Earth. Yeah, and this is all essentially based on triangulation. So if you have a receiver such as this, what you are measuring is distance to satellites, and then by basically communicating with multiple satellites, you get a distance to each one of those satellites, and then based on these distances, you can triangulate the position of the receiver. This is also in 2D shown here, so maybe if we know the distance to this satellite, here given as the red circle, distance to this satellite given as the green circle, and distance to this blue satellite, this satellite given as the blue circle, we can see that based on these distances, the location of our receiver is somewhere here. And as you can see, the circles are not fully overlapping into just a single point. I mean, and this is because there is always, of course, some measurement error when it comes to basically estimating that distance between the receiver and the satellite. So it's and in practice, you basically need at least 4 satellites to solve the position of the receiver. Now, if you are talking 3D positions, it would intuitively make sense that we would need 3 satellites, which would give us 3 equations, and then solving our pose as in x, y, z, 3 variables. But because there is always some clock error that present, you always need at least 4 satellites in practice to compute the position of a receiver. And still, just 4 receivers, that will give you quite a poor estimate for your location. In practice, you typically want to have at least 10 visible satellites to get an accurate position estimate. accurate position estimate with regular GNSS maybe being somewhere in the range of 5 to 10 meters. But okay, so as said, regular GNSS will generally give you like a good accuracy for that system is somewhere like 5 to 10 meters, having multiple satellites in view and so on. When it comes to satellites in view, nowadays many systems are using something even up to 20 satellites when computing that position. But there is a sort of limited accuracy that you can achieve if you are just using a standalone GNSS system without sort of any accuracy enhancements. And there's multiple ways to enhance the standalone GNSS systems, increasing the accuracy. One of them being this differential GNSS, DGNSS, where basically we improve the position estimate by getting some extra information of for example, the atmosphere conditions. And the basic idea is that we have a base station which is also communicating with the satellite. And if we have a base station with a known location, we can use this information to come up with additional correction factors that we use in our GNSS system. So these are a simple DGNSS system. Basically, you have a base station, you have a receiver or a client who is actually doing the positioning, and then based on communicating with the satellite, the base station with the known position calculates these sort of different error metrics, different parameters that can be related to, for example, how the atmosphere bends the signal. And these are basically sent typically via internet to the DGNSS receiver that then uses these corrections for more accurate positioning. With the DGNSS system, with sort of good visibility of satellites, you could expect maybe a localization accuracy of maybe 1 to 2 meters, or even half a meter to 2 meters. But okay, even if we want to refine our positioning even further, a common way to do this is real-time kinematic RTK GNSS. And what this basically is, that it also uses a base station, similar to DGNSS, but it's also applying more advanced signal processing techniques. So whereas your typical standalone GNSS and DGNSS, it's basically based on the simple time of flight calculations. So basically, you have the signal that is going between the satellite and the GNSS receiver, traveling at the speed of light, and basically based on the time that it takes for that signal to travel, you can compute the distance. But when in RTK GNSS, we add some extra processing to this. Namely, basically, we are looking at the actual phase of the signal, which we then use to very accurately determine the distance that the signal has traveled. But okay, and probably an important thing to mention that with RTK GNSS, in good conditions, you can reach accuracies of even as accurate as some centimeters in good conditions. So basically, standalone GNSS, we are talking about errors of, let's say, 5 to 10 meters maybe. These are, of course, approximations. With differential GNSS, our error could be maybe 1 to 2 meters. And then with RTK GNSS, we are maybe talking about some tens of centimeters of error. But these values are typically applicable to somewhat reasonably good positioning conditions. And okay, what does it mean that if you have good positioning conditions? This is basically GNSS is prone to quite different sources of error. One major error in urban environments being these urban canyons. So as I was talking about, when it comes to good conditions for satellite positioning, you want to have a high number of satellites visible. So you want to have a good open view of the sky. Like ideally, you would be in the middle of a field, and this is maybe why autonomous agricultural machines rely quite heavily on GNSS. But okay, if you're operating in a city type of environment, or let's say even in a forest, your visibility of the sky might be limited. For example, due to being surrounded by tall buildings. And what this essentially causes is that suddenly you don't have so many satellites that are visible. And the satellites that are visible, they might come from very specific angles. So ideally you would want to have a high number of satellites visible from very different angles at the sky to get the most precise positioning. But in urban environments, many satellites can be blocked, and the ones that aren't blocked are come from very specific, narrow directions. Yeah, and another important problem in urban environments is this multipath problem. Also typically caused by surrounding buildings. So if essentially you have a satellite here and a receiver here, and you would want to be measuring this distance here, sometimes it can happen that actually the signal that you're receiving is coming from the satellite and being reflected from some nearby buildings or other types of obstacles. And of course, if your signal is being reflected like this, then the distance that the signal is traveling is also longer, and thus hampering your positioning. But yeah, there's also other types of errors. Maybe there is some interference coming some interference coming from some other some sources. There might also be atmosphere errors. So if we are measuring the time that it takes for the signal to reach us from the satellite, basically dependent on the conditions of the atmosphere, those might affect the speed that the signal is traveling. And then you also have these sort of problems that are basically, I mean, someone might be causing your GNSS positioning issues on purpose. This is something that has been quite a lot on the news in recent times. So when it comes to sort of intentional interference of GNSS signals, there's basically two main types. So you have jamming, which is basically just someone blocking your communications. I mean, essentially at the frequencies that your receiver is using, someone is just sending a lot of noise on those frequencies, preventing your receiver from being able to communicate with the satellite. The result, of course, is that if you can't communicate with the satellite, then you're not able to do any positioning. And this is a sort of a common way to basically prevent GNSS localization. Then the more elaborate way is basically spoofing, where some external agent is basically pretending to be a satellite and communicating with the receiver. This is quite a bit more difficult to implement, but it's also more dangerous. Because whereas with the jamming, you are not able to be able to communicate with the satellites, and you know that, okay, my positioning is compromised. In spoofing, someone is basically sending you incorrect data on purpose. And you might not know that the GNSS positioning is compromised, you're just getting incorrect data. So this is more difficult to implement, but it's also quite a bit more dangerous. But okay, that was briefly about GNSS. I think sort of the summary to take from that is that GNSS can provide us positions sort of all over the globe, but I mean, very conveniently all over the globe, but it comes with the sort of downside that it's not very reliable or not very accurate. Or when it is very accurate, it's typically not very reliable. So we have other ways then, of course, to locally localize ourselves. So something you can use for localization is basically inertial measurement units. So basically, inertial measurement unit, typically what you have there is an accelerometer and a gyroscope. You might also have a magnetometer in there to help you with localization. Basic operation principle. I mean, with gyroscope, you know how your pose is changing, and with an accelerometer, you can basically measure distances traveled by integrating the accelerations. And with the magnetometer, of course, you can then estimate your position relative to the magnetic field of Earth. But okay, the problem with this technology is typically that errors accumulate over time. So if you are integrating accelerations, I mean, all errors in the acceleration measurements, those are basically accumulated into your position estimates. So IMUs can be very good, but they are commonly used in sensor fusion with other positioning technologies. For example, GNSS fused with IMU is a very commonly used example of this. So basically, for example, if your GNSS system runs into some trouble, maybe momentarily the positioning is not so good, the IMU can help you out, providing you accurate short-term estimates of your position. And there's also, of course, many ways to basically perform this sensor fusion, essentially getting the best out of all the sensors. And IMUs IMUs, similarly to GNSS, are generally cheap components that you basically find in most automated vehicles or outdoor automated robots. But okay, a bit similar to IMUs, another maybe a bit vehicle-specific way to get position estimates is wheel odometry. So very simply put, based on the rotation of our wheel and then knowing the radius of our wheel, we can estimate basically the velocity and then also our basically linear velocity, and from that our position. So very simple way to roughly approximate how the vehicle is moving. Then how well this works, it of course depends on how accurately our wheel rotation is linked to the linear velocity. I mean, for example, if we are operating on very slippery surfaces, maybe if we are operating an autonomous mobile robot in a very muddy environment, or we have an autonomous car driving on icy surfaces, there is typically some slip there, and this of course then causes errors in the wheel odometry. And of course another problem with this, similar to IMUs, is that errors accumulate over time. But wheel odometry is generally another very good addition to use in fusion with other localization techniques. So for example, sensor fusion with GNSS, IMU, wheel odometry. All of these sensors have their downsides, but fusing them together can provide very well functioning localization solutions. But okay, that was basically many different localization techniques, kind of how to use them for localization, what are their pros and cons. But overall, those discussed localization techniques, generally you cannot trust on them to give you sort of centimeter level localization, which is something that in many cases you would want to have when operating your mobile robot or automated vehicle. Because in order to do decision making, many times you need to know your own position very accurately, respective to the world. And now how this is oftentimes implemented is with technology called simultaneous localization and mapping, so SLAM. So what we are talking about here is basically positioning the vehicle relative to a map, and also updating the map at the same time. So a key sensor, basically when it comes to simultaneous localization and mapping, is LiDAR. So oftentimes SLAM is implemented with the point clouds generated by a LiDAR. And basically common way to implement with a 2D LiDAR. With a 2D LiDAR, you get some information like this, highly useful for indoor environments, something that, for example, your vacuum cleaner robots might be using. And then with 3D LiDARs, your information can look something like this. Basically, 3D LiDARs very commonly used for outdoor SLAM tasks. Yeah, and the SLAM can also be generated with other sensors, but LiDARs are a very common choice because they are providing very accurate 3D information of the surrounding environment. Okay, so here's a video of what SLAM looks like in practice. So let's start this from the very beginning. We can see that we have a mobile robot here, and then it has basically a forward-facing LiDAR generating this point cloud environment here. And we can see that first we kind of initialize our SLAM algorithm by getting some LiDAR data and then just putting this on a map. So we initialize taking the point cloud and just establishing that, okay, we will start the map from here. And then you can see as the robot starts moving, it's basically taking more and more point cloud measurements of the surrounding environment and then appending these together. So accumulating the map as it's moving, at the same time localizing itself. So the key idea is that based on the sort of initial information that was received from the LiDAR, the robot takes a new scan with the LiDAR, then basically registers that point cloud to what it has seen previously, thus computing its own position, and then adding the new point cloud information to the map. So we are talking about a procedure where you first get some LiDAR data, then you localize the robot based on matching that LiDAR data to the existing map. And once you positioned yourself, you can then use that new LiDAR data, the parts that have not been previously present in the map, to update the map. So the basically you are always comparing your current point cloud scans to previous information, positioning yourself, called point cloud registration, then updating map with the new information. And of course, then if we have an existing map, then with sort of similar methodology, we can just do localization. I mean, skipping the map updates and just taking in LiDAR scans, matching that to the information in the map, and inferring our position like that. Okay, but now let's break this down. So that was the overview of what SLAM looks like on a LiDAR. Let's now break it into very simple steps so that you will be able to implement your own SLAM or more precisely point cloud registration algorithms. So our problem looks like this. We have some world coordinate system here denoted with the capital X and Y, and we have an existing map. So we have some points here. These are some points that, let's say, based on our previous LiDAR scans, we have created this map. So in the black dots, we have a point cloud that is representing the map in world coordinate system. And now we have an autonomous vehicle with a LiDAR, a 2D LiDAR, and it gets a new scan from the LiDAR. And the scan looks something like this. Remember, this is a simplified example. And of course, because this data has been collected from an onboard LiDAR sensor, all of this information is in the vehicle's coordinate system, denoted with the lowercase x and y here. So now our problem is formulated in such a way that we have our LiDAR scan, the data that our vehicle was seeing, and in the map we have the point cloud information in the known world coordinate system. So now what we would like to do, we would like to know the position of this vehicle in this world coordinate system by matching this point cloud information to this point cloud information. So essentially we are talking about a coordinate transformation that basically gives us, we are talking about a transformation from the vehicle coordinate system to the world coordinate system, so that we will then exactly know the transformation or the vehicle pose in the world coordinates with this transformation. And this is our problem now in 2D. So we what we want to figure out is basically the x and y coordinates of the vehicle in the world coordinate system, and also the heading angle of the vehicle. And then, of course, kind of our correct solution, kind of visualized very simply, looks something like this. So if we take our LiDAR scan and we match it to the map information, which would look something like this, then we can basically see that, okay, this is actually our vehicle position. And now we want to find the transformation which gives us, which gives the coordinate transformation between these two coordinate systems, which then gives us the pose of the vehicle. But okay, let's get into let's tackle this now. After that intuitive explanation, let's tackle this a bit more mathematically. So our problem is so that we have the vehicle, the information of the vehicle LiDAR scan. We have the point cloud here in the vehicle coordinate system, and we want to find the rotation and the translation which then matches this information to the map information in the world coordinate system. So we want to find the translation, which is then the x and y coordinates of the vehicle in the world coordinate system, and we want to find the rotation, which is basically the heading angle of the robot or vehicle in the world coordinate system. And we do this by finding a transformation which transforms this LiDAR scan to or which matches this LiDAR scan to the map information that we have. Now, when it comes to the solution, okay, the first thing that you start thinking about when it comes to matching these points here is that it's quite straightforward to do this if you know the point correspondences. So here you can quite intuitively see that, okay, with this toy data that we have, this point matches to this point, and then this point matches to this point. In real world, you don't know this, but if you are able to find out these correspondences, then the problem becomes quite simple. So essentially, we have the scan points, so our LiDAR scan here, basically denoted by this set of points, the set being S, and then each of these points is then basically x and y coordinates in the vehicle coordinate system for each of those points. And same for the map points, M, but these are, of course, the map points here in the world coordinate system, each one of these instances being a coordinate pair, uppercase x and y. And now, mathematically, this essentially becomes an optimization problem where we want to find the rotation matrix and the translation vector, which minimize this here. So basically, we want to minimize the distance between the map points and the scan points that are transformed with the rotation and the translation. So this here being the sum of the distances between all those corresponding points. And now let's crunch some of those mathematics of how you would actually do this. We will go into more detail about this in the exercises, but let's go through the overview of how you would go about basically finding the transformation, so essentially the rotation and the translation, which minimize this objective function. And the solution is based on singular value decomposition, SVD. But okay, so we want to minimize this, and we are subject to the constraint that R is a rotation matrix. So how you basically start this solution? By the way, you can check out this source to see a sort of more expanded version of this description. You start by computing centroids for those point clouds. So first you take your map points and you compute the centroid for the map points, and then for the scan points you do the same thing. So you compute the centroid of the scan points. And after doing that, you basically center both of those point clouds. So basically you take the map points and you center them relative at that centroid, and you do the same thing for the scan points. What you do after this is you compute the covariance between those centered point clouds. You can see the equation here. You have the centered scan points and the centered map points, and you compute the covariance matrix for these points. Here is the same in matrix notation. But okay, then comes the sort of mathematically tricky part, but luckily for us, a quite simple part, in the sense that next what we have to do is for that covariance matrix H, what we want to do is we want to generate the singular value decomposition of that. Mathematically, this is of course a bit complicated, but luckily with tools such as NumPy on Python, you can compute this singular value decomposition with basically very short, essentially one line of code. But okay, so you have the singular value decomposition where you have the matrix U, then you have the singular values, and then you have the matrix V. And what you want to do then is basically for this matrix of V times U transposed, you want to compute the determinant of these orthogonal matrices. And the reason for this is basically that this will come in handy in ensuring that we as a result of this we will get a proper rotation and not a reflection. And the way you use this is by looking at the determinant. Okay, but then comes the actual step of computing the optimal rotation matrix, which ensures our optimal registration solution. And you compute the R such as this, where you have basically the matrix V, the matrix U, and you also have this matrix here to ensure that we are getting a proper rotation. So basically, if we would not be getting a proper rotation, we would be getting a reflection, then the determinant would have a value of -1, and then this matrix here in the equation would basically then ensure that the outcome is a proper rotation. If V times U transposed is already a proper rotation, then this essentially becomes an identity matrix and it doesn't do anything. But this part of the computation is important for just in case the singular value decomposition is resulting in a reflection matrix. But okay, the result here R is then the optimal rotation matrix for solving this registration problem between the scan and the map. So after this, what is left is then computing the optimal translation vector. And how we do this is basically based on the already solved optimal rotation matrix. So basically, we take our optimal translation is the centroid of the map point cloud. The difference between the centroid of the map point cloud and the rotated centroid of the scan point cloud. Yeah. And with this, we've now solved the optimal rotation, the optimal translation, and what this gives us is basically then the optimal transformation for matching that scan to that map information. And at the same time, it gives us then the position of our vehicle that measured the scan. But okay, these descriptions have now applied to the sort of ideal case where you know the point correspondences. So you already know which point corresponds where, and you are able to formulate this problem as a simple optimization problem of minimizing this function. Now, of course, in real world, if you just have some LiDAR data and some map data, you don't know these correspondences. So what do you do then? What do you do then is basically this approach to solving this issue is called ICP, iterative closest point algorithm. And the core idea of how you can estimate the point correspondences. I mean, you start off with some data like this. So you have the scan, the LiDAR scan from the vehicle. You have the point cloud map, and you have no idea which point corresponds to what. So this point here, it could be corresponding to this point, this point, this point, or any of the points. We have no prior information. So what you do is basically then based on some initial guess of the vehicle position in the world coordinate system, you basically match each point in the scan to its nearest point in the map. So if our initial guess for our vehicle position would be like this, then our situation would look something like this. And then to estimate the corresponding points, we would take each scan point and we would then say that it corresponds at the nearest neighboring point in the map. So for this point, we would have it here, for this point here, and so on. And we can, of course, then see that we run into the situation that not all of our estimates are correct. And some points might be matched to the same point. Yeah, but anyway, this of course doesn't give us the perfect solution, but it gives us a sort of some initial idea of which points could be connected to one another. And then we use an iterative approach. So iterative closest point algorithm. So we always find the closest points. We assume that those are the corresponding points, and then we basically run the optimization that was just shown previously with known correspondences. And with that, we find an updated estimate for the transformation, so the rotation and translation. And with this updated estimate, we basically then get a more accurate estimate of the vehicle position, and then we do the same thing again. So we keep iterating until we find a suitable solution. So now our solution got us a little bit closer, so we can see that the points are quite a bit better matched, not still optimally, but yeah, we basically keep iterating this, matching all the scan points to their nearest map points, running the optimization with the point correspondences, finding a transformation, applying that transformation, and then iterating again. So now with this next iteration, we might result in a solution that is almost optimal. And then that iteration is basically repeated until some criteria is fulfilled. You might have a criteria basically saying that okay, when all the scan points have a sort of nearest point in the map that is suitably close, you can then stop the iterations and conclude that you have found the optimal solution. And this is the iterative closest point algorithm. There are much more advanced methodologies for basically this point cloud registration problem, but this is a sort of a very intuitive first method to learn, because it's quite intuitive to understand. And of course, if we would be running a SLAM algorithm, we would always be using this registration for finding out the vehicle position, and then updating after matching the scan to the map information, adding new points to the map, and running the algorithm like this. So this would be a very straightforward solution to running SLAM. But okay, that was ICP, basically straightforward, simple to understand algorithm for point cloud registration, which allows straightforward implementations for SLAM. But of course, SLAM has been a subject of extensive research, and there have been a wide variety of very advanced methods implemented for the SLAM problem. One very important one to mention is this normal distribution transform, NDT. This one is quite commonly used because it's very efficient in terms of computational load. So ICP, since it's doing point-by-point matching, it gets quite computationally heavy, since with these LiDAR scans and maps, we are generally talking about the tens of thousands, hundreds of thousands of points, and so on, resulting point-by-point comparison being very heavy. Now what NDT does, essentially, it basically compresses these point clouds into sort of a piecewise normal distribution representations, which makes this registration quite a bit more efficient. Another sort of family of SLAM approaches are particle filters, which are essentially these probabilistic SLAM approaches, kind of modeling the process probabilistically, enabling estimation of uncertainties and so on in the localization and mapping, and therefore being very good for many applications. A sort of commonly used example here is fast SLAM. Another family of approaches is this feature-based approaches. What these generally do is, instead of comparing the point clouds point by point, what they do is they extract specific features from the point clouds that they use for registration. For example, this LOAM uses different geometric features such as edges and planes to perform the registration and SLAM. And also a good example here is point-to-plane ICP. So instead of this typical point-to-point ICP, point-to-plane ICP basically takes advantage of planes that are found in the point cloud. And one important thing to mention are these graph SLAM approaches. So now I've been talking about registration and quite simple approaches to SLAM. So doing the registration and adding the new points and being happy with that localization and resulting map. What graph SLAM does, it effectively builds a graph network of the SLAM problem. So all the locations, the poses of the robot are basically compiled into this graph network, which can then be optimized with graph optimization tools, which is very useful for things such as loop closure. So when we realize that we are arriving to a point that we've previously visited when running SLAM, we can use that to correct for drift and other errors that might have occurred previously. And with GraphSlam, since you've built this graph network of all the poses leading up to that point, you can run these optimization procedures that then basically look at the historical data and increase the accuracy of the previous localizations and the current localization and the resulting map. And sort of a final thing to mention, as with most techniques in autonomous vehicles, autonomous robotics, machine learning approaches are something that are very much a current trend right now in many tasks, showing the best performance, and similar applies to many SLAM tasks. So deep neural networks and other data-driven methods are showing very good performance to these SLAM tasks. Kind of different approaches compared to these sort of traditional modeling-based approaches. The machine learning approaches, of course, offering good performance, but coming at the cost of being these sort of black box solutions. But okay, now we've been talking about SLAM with point clouds, which is typically something that you do with LiDARs. Other types of point clouds like stereo cameras as well. But let's talk a little bit about visual SLAM, VSLAM, which is another type of another way to run SLAM. And basically the idea here is that we are running these camera-based approaches, mostly used due to the reason that cameras are quite a bit cheaper than LiDARs. But okay, let's look at a video of this VSLAM to see what it's all about. Now in this video, there's fusion between a camera and an inertial measurement unit. And here on the right, you can basically see this video input, and from the video there are certain key points being extracted that are basically shown with these green markers. Here on the left, you can see the SLAM results running in real time, the green triangle pyramid type of thing being the camera, and then these blue markers being sort of previous camera poses. And let's take a quick look. And then here in the red points, you can see the point cloud that is being reconstructed of those features. And skipping a little bit ahead, you can see that now in this video they are basically exploring this office area, going through the corridor from room to room, and you can see the algorithm running here. Just simply based on a single camera view, so monocular camera and an inertial measurement unit, they are capable of running this SLAM, performing this localization and mapping at the same time. But okay, so VSLAM is basically SLAM with cameras. The main motivation typically being that cameras are low cost as opposed to LiDARs, which tend to be very accurate, but are generally quite expensive. And this VSLAM, it can be operated without any sort of inherent depth information needed, such as stereo vision. Instead, what's being done is we are using multiple consecutive images to reconstruct the 3D shape of the environment. And so basically 2D images, basically sequence of 2D images is enough for VSLAM, but typically there are other sensors included as well, quite commonly IMU. This makes the process more accurate, and at the same time it allows extraction of the scale of the scene from the SLAM pipeline, because even though the consecutive 2D images are enough to model the 2D shape, the 3D shape of the environment, the problem here is that with just monocular images, you are not able to reconstruct the scale of the environment. intuitive way to think about this is basically if you have a single camera that is moving around in a scene, you cannot know whether you are looking at essentially a miniature model or sort of like real life scale models. So you can extract the shape, but you are not able to extract the scale of the scene. For that, you either need additional sensor information such as IMUs or some sort of scene, some sort of advanced scene understanding. For example, doing reconstruction on these type of scenes, knowing the size of passenger vehicles, we could use that information to extract the scale. But that's important to note. And sensor fusion is typically done because just using cameras generally results in lower accuracy in the SLAM pipeline. So cameras are cheaper, but they are generally less accurate than LiDARs. One example of a commonly used VSLAM method is OrbSLAM. And here's also a video of some VSLAM research published, some years ago already, but kind of goes to show what the technology is capable of. So this video here, it doesn't include any types of other sensor fusion. It's basically just monocular images. So video from a single image. Video from a single camera, that is taken from this traffic scene, and you can see that with algorithms they are capable of localizing and constructing a map of this environment. But okay, so then what type of steps are then needed for running this VSLAM? The answer is quite a bit more complicated as opposed to the point cloud and point cloud ICP registration that I was showing in the previous slides. So we won't go into details here, but I'll tell you sort of in a general way the steps that are needed when running a traditional VSLAM algorithm. Now, the traditional VSLAM pipelines often start with this feature extraction and feature matching. And this is basically highlighted here. So now if we imagine that we have these two images of the same scene, what we start off with is finding sort of key points, image features. These can be SIFT, SURF, ORB. You can look into this in more detail if you're interested. But the idea is that we get this sort of unique key points from the image, and then in the other image we then find the same key points and match them to one another. So now we have these corresponding key points from both images. And then basically based on this information we are able to compute the camera poses up to scale. So our translations are only up to scale. We get rotations and translations for which we don't know the absolute scale. But anyway, in this representation, here we have the images, that both of these images. Here the red points represent the 3D shape of these key points in the real world, and then in blue we then have the key points in the images. But without going into details, based on this information of the matching key points, we are able to compute the relative camera poses behind these two images. And basically after we've solved those camera poses, we can use that information to then basically triangulate other points within the images into the 3D scene. And this is the general steps for a basic VSLAM implementation. So you have feature extraction and feature matching between two images. Then you use the geometry to compute the camera poses, and then the camera poses can be used to then create 3D information out of the pixels. But okay, that was sort of like the minimalistic examples of how to implement this VSLAM. Now some, let's say, kind of more details behind this. So kind of a very important thing to note, like previous example, I was just showing how to do this for 2 images. In reality, a number of images are typically used and combined together to extract this depth information. So in the case of this football here, we have multiple images that have overlapping information of this side of the football, and then we use these images to basically triangulate best possible 3D information. This is called bundle adjustment. So using multiple images, more than 2 of the same scene to reconstruct the 3D information. Yeah, another thing that very oftentimes GraphSlam techniques, bundle adjustment effectively could also be considered a GraphSlam technique, but these are often used with VSLAM approaches. Since VSLAM is not quite as accurate as LiDAR-based approaches commonly, this means that it's very important to include these graph optimization techniques to ensure that the localization and the mapping are basically done in the most accurate manner possible. Yeah, and again, as applies to many autonomous vehicle technologies, deep learning methods are kind of dominating the state of the art of VSLAM approaches, since they generally demonstrate excellent accuracy and performance. But still, the overall LiDAR-based SLAM is generally more robust and accurate than these camera-based approaches. Yeah, and now I've been talking quite a lot about how you can do this VSLAM with just monocular images to kind of highlight the possibilities, but still another reminder that typically you want to fuse some other sensor information in the pipeline as well to get accurate results. Yeah, and these VSLAM techniques can also be combined together with stereo vision, and then kind of combine the depth information with these visual clues in the localization and mapping process.